Hi, grade 11 and 12. Welcome to this session. Thank you very much for joining me today. Today we're going to be focusing on grade 11 to 12 Euclidean geometry. It's a revision, and today we're going to be starting with Theorem 1 and its converse. Hopefully you'll enjoy this session, and let's go. Okay, before we move any further, let's start with key geometric Euclidean geometry basics, right? So this is really the prior knowledge that you must have for you to be able to understand this theorem that we just gonna be discussing and explaining within this session. Okay, so number one, we must understand the idea or the knowledge of lines and angles. What comes to your mind when you think of lines and angles? Obviously, you must be thinking of what? Of straight line angles, or rather adjacent supplementary angles, right? To say angle in a straight line, angle B1 plus B2 is equals to what? Is equals to 180 degrees. So this is one of the key basics that you must be having for you to be able to understand this, right? So we know that if we add angles on a straight line, we're going to get what? 180 degrees. And what's the reason for that? The reason is that angles in what? In straight line, right? So that's our reason. Angles in what? In a straight line. So, or rather someone can say angles in straight line are supplementary, right? Okay. So number two, vertical opposite angles. What comes to your mind when you think of vertical opposite angles? Okay, we know that vertical opposite angles are what? Are equal, right? So vertical opposite angles are equal. So if you have lines forming that sort of like X shape, you know that those vertically opposite angles will be what? Will be equal. And our reason for that will just say vertical opposite angles, right? Vertical opposite angles. Okay, let's go number three. Very, very important. Alternate angles. What do we know about alternate angles from grade 9? Is that alternate angles are also what? Are also equal. And what are alternate angles? Maybe let me use a different color, maybe yellow. Alternate angles are those angles that are inside the Z shape, sort of like a Z there, right? So they are alternate, they're in different position, they are alternating, right? So we say those angles are what? Are equal. Someone can identify it like this, so long as this line is parallel to this line, right? So that's what we are very interested in. Then we can deduce that, oh, alternate angles are equal. So someone can do like this. Okay, so to say this angle is the same as what? As this angle. And our reason for that is just alternate angles are equal. Okay, so long as you have that Z shape there, you just equate the angles within the Z shape, sort of like this one. So this angle will be equal to this. If it's like this, this angle will be equal to this, right? So long as this line is parallel to what? To that line, we can deduce that, oh, alternate angles are equal because we can see AB is parallel to what? Is parallel to CD. So that will be our reason. Okay, so let's go. Number 4, angles around a point, right? Angles around a point. What do you know about angles around a point? They all sum up to 360 degrees. So all angles around a point will sum up to 360 degrees because this is sort of like a circle, right? And for you to make one rotation, you have to make 360 degrees. So hence A plus B plus C, angle A plus B plus C equals to 360 degrees by the reason angles around a point, right? Angles around a point, and that's the reason you give. Okay, number 5, corresponding angles, right? What are corresponding angles, and how do we know that this is the case in this case? So you must have parallel lines, and it's quite similar to alternate angles, right? Because we also we can't say if you just have a lines like this, you can't come say this angle is equals to this because they are alternating, they form Z, something like that. then you say they are equal. If these lines are not parallel, right, you only say alternate angles are equal if the lines are parallel, and that's the case, right? Similarly with corresponding angles, you must have parallel lines, and they showed you using this symbol. Let me just highlight it for you. So if those lines are parallel and you have angles in a form of, maybe it can be F, it can be T, right? So this angle being equal to this, if it's F like that, that angle equals to this. So they are corresponding, they are in the same position, right? They're in the same position. Like here, you find that this angle is equals to what? Is equals to this angle. It means that those alternate angles are what? I mean, corresponding angles are what? Are equal, because they are corresponding. They are not alternating, sorry. But they are corresponding. They are in the same position. They are corresponding. So we can deduce, oh, those angles are equal, because what? Corresponding angles are equal. And we also have to mention which lines are parallel, because AB is parallel to what? To CD, because AB is parallel to CD. Lastly, but not least, co-interior angles. Okay, co-interior angles. What do we know? Remember, this is very, very important key geometric basics that you should be able to that you should understand before we start with revising these theorems from your grade 11 to 12 transition. Okay, so co-interior angles, what do we know about co-interior angles? Is that they are supplementary, and similarly to what? To corresponding angles, similarly to alternative angles, there must be parallel lines before you say these angles are co-interior, right? There must be parallel lines, and we can see this line is parallel to this one. So when you see parallel lines, obviously you must think of three things. Is there alternative angles? What do I know about them? They are equal. Is there corresponding angles? What do I know about them? They're equal. Is there co-interior angles within those parallel lines? What do I know about them? They're supplementary. And what does it mean? They add up to what? To 180 degrees. And those are angles in a form of a U. If this and this. Or let me say if you have A there and you have B there, and this line is parallel to this. That's a key condition, right? So we can say angle A plus angle B is equals to what? Is equals to 180 degrees. And what's the reason? Because they are co-interior angles, and you give them the lines that are parallel. Maybe if this was line CD and this was line EF, right? So you will also give them that, because CD is parallel to what? To EF. You don't just say co-interior angles are supplementary and you don't show them which lines are parallel. They are co-interior angles, and they are supplementary because they are within parallel lines, and that's the condition that you should never leave it when you are doing this. Okay, similar to this, they give us X and Y. They're in the form of that shape that is like U, right? So you know that this angle and this angle will add up to what? To 180 degrees. And you just say co-interior angles are supplementary, or you just write co-interior angles. You also give them the lines that are parallel. Very, very important, because you can't have co-interior angles without having lines that are parallel. Okay, let's move. Okay, let's also discuss some of the key geometric basics. We have triangles, right? Triangles, these are some of the knowledge that you have to know before we start introducing grade 11 to 12 Euclidean geometry. So triangles, you have different types of triangles. You have scalene triangles that has no sides being equal, right? So all their sides are unequal. As you can see, this line is not the same as this one, and this one is not the same as this one, as it's not the same as the first one. So that is a scalene triangle, no sides equal in length. Very, very important. You have an isosceles triangle, right? So this is one of the most important triangles, because in Euclidean geometry, they give you questions where they just put some diagrams and give you some of the isosceles triangle. They won't tell you this is an isosceles triangle. You have to check it for yourself, right? And these are the things you look at. So you can have two sides being equal. Then you'll be able to deduce, oh, this is a isosceles triangle, right? Two sides being equal. Then what do we know? If two sides are equal from that triangle, also the base angles will be what? Will be equal, right? So if this is angle A and this is angle B, and this is C. So if we have that AC is the same as BC, right? If we are given that, then we can deduce that therefore angle A will be the same as angle what? Angle B. And what's our reason for that? Someone can say base angle of isosceles triangle, right? Or rather someone can say equal angles opposite equal sides, right? So equal angle opposite equal side, or someone can say angles opposite equal sides, right? Angles opposite equal sides, right? So the angles that are opposite, they're equal because they have equal side. I think this one will be a good reason, right? So you can choose to just say base angle of isosceles, or rather angles opposite equal sides, right? So that's an isosceles triangle. Then we have an equilateral triangle where you have all sides being equal, right? And what we know is that all those angles will be the same as 60 degrees, because the sum of angle of a triangle, they're equals to what? 180 degrees. So 60 plus 60, 120 plus 60, 180. So because all sides are equal, right? Very, very important. You have right angle triangle, right? And what comes to your mind when you think of right angle triangle? You must think of what? Pythagoras theorem, right? And we cover Pythagoras theorem in one of our sessions. I will just put down the link to that session on the description of this video. Okay, so what can we deduce from right angle triangle? How do we see it? It has 90 degrees, right? Yeah, it has 90 degrees. What can we deduce? That AC squared, hypotenuse squared, is equals to the sum of the other two sides squared. So it will be AB squared plus BC squared. So that's what we can deduce from there. And we have just this triangle with angle ABC, right? ABC. What do we know? Is the sum angle of a triangle. They are equals to what? 180 degrees. You must not forget. Sum angles of a triangle inside the triangle, they are equals to 180 degrees. And our reason for that is that we just say sum angles of what? Of triangle. And that's the reason you give if you want to deduce that, oh, these are equals to 180 degrees. Okay, then we have exterior angle of a triangle, right? You know that this is an exterior angle. It's outside the triangle, and you have this triangle here. So you can deduce that angle C is equals to angle A plus B. So exterior angle of a triangle is equals to the sum of interior angles in a triangle. Okay, so angle C will be equals to angle A plus B, and our reason is simply exterior angle of triangle, right? Exterior angle of a triangle. You don't need to tell them exterior angle of a triangle equals to sum of interior angle. If you just give a reason exterior angle of a triangle, then that's fine. Okay, so and they're showing you the Pythagoras theorem and how it can be deduced to solve all the sides like that if you have a right angle triangle. Okay, I think let's now move straight to theorem 1. I think we are good to go. Okay. All right, before we quickly go to theorem 1, let's focus on very, very important key geometric basics of Euclidean geometry. So these are basic circle terminologies that we must understand before we introduce the theorem. Okay, so we have something called the radius, right? And I know if you're in grade 12, you're already familiar with this. If you're in grade 11 and this is your first time learning this, I'll have to explain what this is, right? And it's also clearly indicated in the diagram. Just use different colors to show you, right? So in yellow, this is the radius, right? So you can just see a radius is just a line from the center of the circle, right, to any point in the circumference. Okay, so that will be called what? A radius. And what do we know about radius? Okay, is that all radius are equal. NB. All radius are equal. All radius are equal. Okay, so if you have another radius here from the center of the circle to the circumference, just know this radius will be the same as this. Even if you have another one here, this radius will be the same as that one. and this other one is a radius because it's from the center to the circumference. It's equal. All these radius are what? Are equal. All radius are equal. Okay, so yeah. Okay, number 2, we have a diameter. So a diameter is a line that passes through the center of the circle and that joins the circumference of the circle in both its ends, right? So you can see that there's a line passing through the center of the circle. Maybe let me use a green color. Here is it. It passes through the center of the circle, joining the circumference using both its ends, right? So that is called the what? A diameter. What can you say about a diameter? A diameter is made up of 2 radius. This is radius 1 and this is radius 2. And what do you know about radius? Is that all radius are what? Are equal. It means a diameter is equals to R1 plus R2, right? And we know that R1 is equals to R2. Where there is R1, we can put R2. And it's going to be 2R2. And R2, this is just what? Just a radius, right? Because that's a radius. So diameter is what? Is double the length of the radius. So that's what we can deduce from there. So because diameter is just a line passing through the center of the circle, joining the circumference on both its ends, right? So that's called the diameter. Okay, very, very important. I hope you are noting that down. Chord. Let's come to the chord. What is a chord now? So a chord is a line with endpoints on the circumference. It joins both its endpoints on the circumference. But it's quite similar to a diameter, but the difference is a chord doesn't pass through the center of the circle, right? It just passes through any of the points in the circle, but not through the center of the circle, joining its ends, both its ends on the circumference, and we call this what? A chord. Very, very important, right? And you can see that a chord now, if we have a chord, we'll have something called a what? A segment, right? So it divides the circle into 2 segments. This is the minor segment or smaller segment, and this one will be what? Will be the bigger segment, right? So it's done by a chord, right? It's just a line, not passing through the center though, but just passing through any points in the circle, inside the circle, and joining its endpoints on the circumference. Okay, so that's a chord. We also have a tangent, very, very important. A tangent, what's the tangent? A tangent is a line that touches a curve at only one point, touches a circle at one point. And you can see there, we have our tangent, it only touches our circle at one point. And we'll begin to discuss this relationship between tangent, radius, tangents, chords, and all that as we proceed with these sessions of grade 11 to 12 Euclidean geometry. For now, know that a tangent is just any line that passes through, that touches a curve or rather a circle at one point outside the circle, obviously. Because if it comes inside, it won't be a tangent because it will be touching at 2 points. And if that is the case, we now call it a what? A secant, right? So a secant would just be a line passing through 2 points in a circle, right? If it cuts the circle like that, it's what? It's what? It's a secant. Okay. Okay, here's the theorem that we're going to start with on your 11 to 12 Euclidean geometry revision of this chapter. Okay, so this is quite your theorem 1 and is the one for a perpendicular line, right? Okay, so what you have now is that you have a line from the center of the circle. Maybe let me use a different color. A line from the center of the circle that is perpendicular to the, remember we said this is the chord, right? Because it has both its ends on the circumference, but it does not pass through the center, right? So it's called the chord. So you have a line from the center of the circle and it's perpendicular to the what? To the chord. And what does the theorem say? It says if a line is drawn from the center of the circle, being perpendicular, and you can see by 90 degrees there, being perpendicular to the chord, then what happens? then it will bisect the chord. What's the meaning of the word bisect? It's to cut into what? Into half. So in other words, if you have a line drawn from the center of the circle perpendicular to the chord, then it will divide that line into half. In other words, it will bisect the what? The chord, such that you'll have that therefore AM, as you can see, AM there will now be equals to what? Will now be equals to MB. And this is the then part, right? This is the then part, right? And this is the what? This is the this is sort of like the given part, right? So this is after, or rather we can say then. So this is like initially, right? Initially. So what do we know initially? You just have a line drawn from the center of the circle being perpendicular to the chord. What happens then? It says the very same line is gonna divide, then it will bisect the chord. In other words, you'll have AM being equals to MB. And this is simply the theorem that it's called theorem number 1. Okay, so the reason that you give there is what? It's perpendicular from center bisect a chord. That's what you give, right? Some can write like the perpendicular from center bisect the chord, right? Bisect the chord. If you want to write to say AM is equals to MB, right? So anytime if you just have a line drawn from the center of the circle and you find that it's perpendicular to the chord, what you can deduce, this one is also equals to that one. Okay, but let's take a look at the converse of that. Okay, so with the converse theorem, right? So what actually happens with the converse is that the statement that was the then part to say what happens when this occurs now becomes the initial statement, right? So it's sort of like a reverse. Remember, the theorem says if a line is drawn from the center of the circle perpendicular to the chord, it bisects the what? The chord. But then with the converse, now we start at the end of that statement of the theorem, going back to the initial statement. Okay, so what will it be now? It will say if a line is drawn from the center of the circle to the midpoint of a chord. In other words, we are saying if a line is drawn from the center of the circle bisecting the chord. This is the same as saying bisecting the chord. It's just that they just use the term what? To the midpoint, but we know that to the midpoint it will be bisecting the chord. Then what will happen? Then that line will be perpendicular to the chord. That's what happens. So you can see this is sort of like a reverse from the theorem, because the initial theorem says if a line is drawn from the center of the circle being perpendicular to the chord, it will bisect the chord. It will cut the chord into half, or it will go to the midpoint of the chord. But now we are saying if there's a line that goes to the midpoint of a chord from the center of the circle to the midpoint of the chord, in other words, you are given that AM is equals to what? Is equals to MB. And we can see there is a line there going to the midpoint of a chord. What will happen? That line will also be perpendicular to the chord. And this is the converse theorem 1, or rather, you can give the reason to say there is a line from the center to midpoint is perpendicular, right? Someone can say line from center to midpoint perpendicular, right? So it will be perpendicular to the chord, right? Obviously, if you have something like this and you have a line, it's cutting here, they tell you that this side is 3 centimeter, this one is 3 centimeter. You can deduce, oh, this line is actually cutting this chord into 2 equal halves, meaning this part is the same as this one. What does the theorem, the converse theorem say? Then if it goes to the midpoint, then it will also be what? Perpendicular. So there's that 90 degrees there. It will also be perpendicular to the what? To the chord. Okay, let's take a look at some quick example to help you conceptualize this. Okay, a quick example. You are given O is the center of the circle, right? And you have and you can see O is the center of the circle from the diagram. And you have your AC is equals to 8 units. So you can see the whole chord AC there is 8 as indicated. OB is 3. Very, very important. OB is perpendicular to AC, right? So you can see OB is perpendicular to AC because we have that 90 degrees there, right? Okay, so they want you to calculate A. They want you to calculate the length of AB. They want you to get the length of AB. What is the length of AB? This is rather the simplest question, right? We have to recall the theorem. What can we see from the diagram? There is a line from the center of the circle, right? Being perpendicular to the what? To the chord AC. What does the theorem say? A line drawn from the center of the circle perpendicular to the chord will what? Will bisect the chord. And that's theorem 1. In other words, AB will also be equals to what? Will also be equals to what? BC. And we know that the whole length is 8. So if those two are equal, it means our AB is 4 and our BC is also what? Is also 4. Very, very simple question. So we just give them AB is equals to 4. And the reason, why are we saying AB is equals to 4? Because there's a line from what? From center of the circle. And is what? Is perpendicular to chord, right? Line from center of the circle being perpendicular, it bisects the chord, right? So that's our reason. Line from center of the circle perpendicular, it what? This implies that it bisects the chord, right? Yeah, that's the case there. So quite a simple question. Let's go to B. So B, they want you to calculate OC, right? OC. What is your OC there? Okay, let's go and check OC. Let me use a different color. This is OC in green. Can you see? And your OC is your what? Is your radius, right? Okay. What do you have now? You have BC, which is 4. You have OB, which is 3. And what type of triangle is this? Can you see that there's a 90 degree there? So it's a right angle triangle. Remember when we revise triangle basics, we said what about right angle triangle? What must come to your mind is what? Is Pythagoras theorem, right? So we're just going to use Pythagoras theorem to say hypotenuse squared OC squared will be equals to what? OB squared plus what? Plus BC squared. And this is from what? This is from the guy Pythagoras, right? Okay, so our OC squared will be OB, which is 3 squared, plus BC, which is 4 squared, right? So OC will be equals to the root of 3 squared is 9, plus 4 squared is 16. So OC will be equals to the root of 25, which is equals to 5. Quite a very simple question. And you can see that we just use our theorem 1 here in order to answer that. Theorem 1 and what? And Pythagoras. So that's what you have to be thinking about when you get this kind of question. But let's further extend and take a look at quite a different example. Okay, example number 2. They give you O is the center of the circle, and you're given that your AC is equals to 16. Okay, and we can see from the diagram they represented AC is 16 there. All right, and you have your AB is equals to BC. We can see if AB is equals to BC, then we can deduce that AB is 8 and BC is 8, so that when we add them, we get the 16, right? Okay, we have OA is 17, and they are saying calculate the length of OB. Quite a simple question, right? Calculate the length of OB. Calculate the length of OB. How can we get the length of OB? So the first thing that we must do, we can't use Pythagoras theorem before we deduce or tell them that this is a right angle triangle. So we must think of the theorem now. There's a line drawn from the center of the circle to the midpoint of a chord. What do we know about that? It is perpendicular to the what? To the chord. So we must first tell them that angle ABO is equals to 90 degrees. By what reason? Because there's a line from center to what? To midpoint of chord. So to midpoint, and this implies that it will be what? It will be perpendicular. Line from center of the circle to midpoint, or rather you can just say converse of theorem 1, right? Because that's the converse now. If a line from the center goes to the midpoint, we know that it will be perpendicular to the what? To the chord, right? So that's the converse. So after telling them that this angle is 90 degrees, we can now go and use Pythagoras theorem in order to solve for our OB. That will be quite simple, right? So AO squared, which is our hypotenuse, is equal to the sum of the other two sides squared, right? What is your AO squared? It's going to be 17 squared. What is your AB? It's 8 squared plus what? Plus OB squared. Then we can solve for OB squared. So it's going to be 17 squared minus A squared, which is 225, is equals to OB squared. Then our OB will be the root of 225, right? The root of 225. What is our OB? Square root of 225. It's going to give us 15. So then you solve for your OB. That is quite simple, right? Okay, let's look at some quite higher standard example. Okay, let's look at this last example. So they're saying P is the center of the circle with radius of 73 units. Okay, we know that a radius is a line from the center of the circle, right? It's just a line from the center of the circle. Let me show you. From P to R, it's our radius, and they tell us it's 73 units. And M is the midpoint of chord QR, and we can see M is the midpoint because this line is the same as that one. And we can see N is a point on PR, so that PN is 40. So they told us this one is 40. So if this is 40 and the whole is 73, so 73 minus 40, 33 is going to be NR, right? And we are told that MN is perpendicular to what? To PR, and we can see by the 90 degrees there. Okay, so they're saying number one, give a reason why PM is perpendicular to QR. Why is PM perpendicular to QR? In other words, they're saying why is there also why do we also have 90 degrees there, right? And we know the reason for this, right? Because we have a line from the center of the circle and it's to the midpoint of a chord, right? What happens? You must think of the converse theorem to say if a line is drawn from the center of the circle to the midpoint of a chord, then it is going to be perpendicular to the what? To the chord. So in other words, our reason is that we have a line from center to what? I don't know if this is the correct spelling for center, to midpoint of chord. And what does that imply? It implies that it will be what? Perpendicular to chord, right? If you have a line from center of the circle to midpoint of a chord, then it will be perpendicular to the chord. And this we know it as the converse theorem 1 of your grade 11. And as you transition to grade 12. Okay, so that's the converse theorem. There's a line from the center of the circle to the midpoint of a chord, and it's going to be perpendicular to that chord, right? So that's our reason. Number 2, determine the length of MR to the nearest whole number. Okay, we are not given a lot of values here, right? And they want the length of MR. How can we get the length of MR? Using our idea of theorem 1. We know that there is also 90 degrees, right? So if it's 90 degrees, we want to solve for MR, we can use theorem of Pythagoras to say PR squared is the same as what? As MR squared plus what? Plus PM squared, right? So we're just going to use two methods here, right? And this one that I'm doing now is the longest one, right? But I'll just show you the quickest, smallest one using relational understanding from one of the videos that we uploaded on theorem 4 of grade 12 Pythagoras theorem. Okay, I'll just show you after finishing this one. So PR squared minus MR squared will be equals to PM squared, right? So why am I solving for PM? Because I don't have PM. We don't know the length of PM, right? We are not given, so it won't help us. So we just call this equation 1. So we can go again and deduce equation 2 from this smaller triangle here, right? Let me just show you maybe a blue color. This smaller triangle there, right? We can deduce a theorem there. It's gonna be what? MR squared is equals to what? MN squared plus what? Plus or rather, let me use the bigger one, because that smaller one won't help us because it's having another unknown, which is mn, right? We can use the bigger one, this one. We have 90 degrees there, so it will be pm squared because we want to eliminate that pm, right? So it will be pm squared. Check the blue triangle there. Pm squared is the same as what? The same as Pn squared plus Mn squared, right? So where there is Pm, I can go and substitute what? Pn squared plus Mn squared, right? So I'll have Pr squared minus Mr squared is equals to Pn squared plus Mn squared. So I'm just substituting equation 2 into equation 1, right? And I have that equation. But look, we still have another unknown here, which is mn. We don't want mn because it's an unknown, so it won't help us, right? We have to eliminate it. How can we do that? We apply again theorem of Pythagoras. So on the smaller triangle this time around, right? On this smaller triangle, let me highlight it with yellow. That smaller triangle, we can use theorem of Pythagoras. How is it gonna be? It's gonna be mr squared is equals to what? It's equals to mn squared plus nr squared. So we can solve for mn because we want to eliminate it. It's gonna be mr squared minus nr squared is our mn squared. So where there is mn, we can go and substitute that one, right? So we'll end up having what? Pr squared minus mr squared is equals to pn squared plus mr squared minus nr squared. So I'm just replacing this in the position of mn squared, right? So you have now this standard formula that can help you to solve for mr, right? So if I took mr to the other side, or rather, let me write it properly. We have pr squared in red there minus mr squared is equals to pn squared plus mr squared minus nr squared, right? Or we can just simply substitute what we have. What is your PR? Your PR is the whole 73 units. So it's 73 squared minus mr squared. We want mr. What is your PN? Your PN is 40, right? Because we were given it as 40 squared plus mr squared minus, what is your nr? Your nr is gonna be what? 33 squared. So it was very important that we also go and replace that one, right? So if I take this mr to the other side, or rather subtract mr both sides, I will have minus 2mr squared is equals to what? 40 squared minus 33 squared minus 73 squared, right? So it's gonna be minus 4818. We divide both sides by negative 2, then my mr squared is equals to 2409, right? So to solve for mr, we just apply the square root of that. So mr will be the root of 2409, which is 49.08, which is 49.08. But they said round it to the nearest whole number, so this is the same as 49.1, which is probably the same as to the nearest whole number, so it's gonna be 49 because this one is not greater than 5, so it's just gonna be 49 units, right? So that's the answer for MR. You can see this is quite a long process, but what we did is just to apply the converse theorem. You get your 90 degrees here. You apply Pythagoras theorem up until you are able to solve using simultaneous equation also up until you solve for your MR, right? But there's another method. Let me just show you quickly. So this other method is very, very fast, right? You just need you to use relational understanding from one of the sessions that we conducted on Theorem 4 of grade 12, right? So you should have done a Euclidean geometry for grade 12, but I'll also put the link to that video on the description of this one, right? So here is it. So you must take a look at this and you use your Theorem 1, you relate it or you connect it with Theorem 4 of grade 12, which is known as the Pythagoras theorem, right? So not really how you know the Pythagoras theorem, but in a way of saying there are three triangles that are similar to one another if this case is there and if you can see this in your diagram. So this is 73, this is 40, and this is 33. So we know that this angle there is 90 degrees. Or rather, let me use much brighter color to show you which 90 I'm referring to. By the converse midpoint theorem. Sorry, by the converse theorem 1, right? We know that that angle is what? Is 90 degrees. And what can you see? Is that there's a line from a right angle vertex that is perpendicular to a certain line there. Line from right angle vertex perpendicular down there, or rather perpendicular line from right angle vertex. And if you immediately you see that there's a perpendicular line here that is coming from a right angle vertex, then we can deduce that this smaller triangle here in yellow, or is it orange? I don't know. It's yellow. I don't know. It's similar to what? To this triangle here, right? Which is also similar to the bigger triangle, the mother triangle. We can deduce that from Pythagoras theorem. If you go and watch our video on Theorem 4 of grade 12, Pythagoras theorem, we can deduce that, right? To say the smaller triangle is similar to the other triangle, which are all similar to the bigger triangle. So you have three triangles that are similar to one another. What can we deduce from there? It means it's going to be very simple to solve for MN, right? What you can just do is that you relate two triangles because you already know that all the three triangles are similar to one another if this case is there, if there's a perpendicular line from a perpendicular vertex, right? So what can we deduce? Okay, you just go and identify two triangles. So I'm just going to use two triangles that have MR, right? I'm going to use the smaller triangle and also the bigger triangle, this one, this bigger triangle, right? Because it also contains MR. I can't use this triangle here because it does not contain MR, right? So I'm using two triangles that contain MR because I want to solve for MR. And that's how we approach this, right? Using that Theorem 4 of grade 12, right? So what I'm going to do now is that we're going to have MR squared. When you do your similarity and your proportionality and you cross multiply between the two triangles, you know that the two triangles are similar. Or rather, let me write it like this. We know that triangle MRN is similar to triangle which one? It's similar to triangle. We said MRN, and here we know it's 90 degrees. So it's going to be similar to triangle PRM, right? It's going to be similar to triangle PRM, the bigger triangle. So we are saying the smaller triangle is similar to the bigger triangle by angle, right? And also this is coming from, because we know that there's a perpendicular line from right angled vertex, right? From right angle vertex. So from similarity we can quickly go to what? We can quickly go to proportionality, right? So you can just simply write your proportionality without writing that these two triangles are similar, to say mr squared is going to be equals to this side on the similar triangle, which is nr, multiplied by the bigger side on the bigger triangle, which is pr. And why are we saying these are equal? To say mr squared is equals to nr times the bigger side there is because there is a perpendicular line from right angled vertex. So that's why we can make that deduction there. So very, very important. I want you to go back and look at Theorem 4. Like I said, I will put the link of that session in the description of this so that you can connect and you can easily solve for that without using that long method of using Pythagoras theorem, this triangle, what you use simultaneous up until you solve for MR. It's going to take a long time, right? So MR squared, what is your NR? Is 33. What is your PR? Your PR is the bigger one, which is 73, is given as 73. So your MR is just going to be the root of 33 times 7. So we must get the same answer, right, as we got there, to show that this method is also correct, and we really get the same answer, 49.1 unit. If we round it out to the nearest whole number, because it's 0.1, it's just going to be what? 49 units, right? 49 units. And that's the answer. Can you see this is quite a very short method using what? Relational understanding, where we relate this converse theorem. We are relating the converse theorem 1 of your grade 11 to what? To your theorem 4 of what? Of grade 12, of your grade 12. And we have already made the session of that theorem 4 of your grade 12, which is mostly known as Pythagoras theorem, where you have a perpendicular line from a right angle vertex. And that's it. That's your answer. Okay. Okay, grade 11 and 12, thank you very much for joining me in this session. I really appreciate your time, and I hope you really learned something about grade 11 to 12, Theorem 1 and its converse revision, and also looking at the relational understanding, connecting this theorem with Theorem 4 of Pythagoras theorem. I hope you learned something, and looking forward for your comments and suggestion on how we can improve our session as we continue going further. Coming up next is Theorem 2 of grade 11 to 12, and let's meet on the next session. Thank you very much and goodbye.